You're listening to Snyder Associates podcast series, the civil engineering, planning, and design firm focused on thinking beyond engineering to improve the quality of life within the communities we serve. The host of this episode is Paige.
What's included in a flow monitoring process is going to be the flow meter equipment and rainfall gauges. And big point that I want to stress is if you're going through a flow monitoring project, don't just rely on local and national reported data, such as airports. It really makes it difficult for us to process that information and understand what we're trying to do is look at a system response. And if we're getting rainfall reported data that is 10, 15 miles away, really anything that's not local makes it very difficult. I think in Iowa specifically, we see a lot of thunderstorms that are very isolated. I'll give an example of here in Des Moines. We can get a thunderstorm that maybe hits the Ankeny, Urbandale area and gets 2 inches of rain. I live down on the south side and maybe it doesn't rain at all. That just kind of visualizes why it's important to have a local rainfall gauge. Typically, we want a rainfall gauge for the flow monitoring projects that's within 5 to 10 square miles per gauge. Delineating subsystems to target smaller sewer sheds, just trying to pick out where our meters should be to isolate pieces of the system off as we look to prioritize areas that might have higher I&I than others and where we want to actually start with our inspections. This is just some general recommendations here for some approaches that we typically look at the high level when we're looking at planning a flow monitoring project. 1 meter to every 40,000 feet of sewer. There's a lot of variables that go behind the scenes with that. It depends on urban density. There's a lot of commercial, industrial, residential properties. There's certain values that we try to target, but really what we're trying to do is establish enough flow that goes across our flow meter that is laminar, non-turbulent, that's not restrictive from surcharge, and that's given us enough velocity so we get a decent amount of accurate data as we collect the flow monitoring component. And then monitoring period, I think just understanding the goal here, if we're trying to establish how much clear water is in our system, we want as much wet weather activity as possible. Typically, we'll do a 3-month monitoring period, whether that's in the spring or the fall, depending on where you're located, but really trying to capture some thunderstorm data to project out some of that peak inflow and those infiltration values. I've got a couple flow analysis techniques that I want to go through that are really high level overview of what's out there and what we typically look at. Main goal, we're trying to quantify sewer flows, dry weather, inflow, and infiltration. We're using that rainfall depth and velocity to create ratios and project out values for different theoretical storm occurrences. We're using graphical displays of information to understand thousands and thousands of rows of data and just creating that graphical output that we can understand from the engineering level what the flow data means, and then existing and future projections. Inflow coefficient, Q versus I, we're referencing the rational formula for runoff, and we're replacing that runoff coefficient with the KP value. And that KP value is representative of the average coefficient solved for based on the storm characteristics. So you're getting a ratio of the flow, the intensity, and the area. And we're selecting storms that have a certain KP value. Other criteria that we're using to actually select storms is going to be based on the amount of depth of rainfall that we received over the sewer shed. Typically, we'll look for anything greater than a 1/4 inch just because we want to see that system response, and you can kind of get some diluted data if you include anything less than that. It does affect your trend projection as we plot Q versus I. For those that aren't familiar with those theoretical storm events, typically we're looking at projecting out up to a 100-year storm event, which would be a rainfall that here locally in Des Moines would be over 7 inches of rain in a 24-hour period. There's a 1% chance of that occurring in any given year. So we're trying to optimize what do we need to size our system to. Obviously, I think sizing to 100-year is economically difficult. So we're typically targeting a lower frequency storm to do that. And this is just allowing us to understand what the capacity of our system is with these projections. RTK is another method that we will use to evaluate peak flow in our sewer systems. This is an accepted EPA-approved method. They have a toolbox that you can access online that has pre-developed spreadsheets where you can input data to help with some of the analysis. What do these acronyms mean? The R value is going to be the fraction of rainfall over the sewer shed that enters the collection system. T is the time to peak, and K is going to be the ratio of time to recession to time to peak. How this system works, it's essentially a spreadsheet tool that we can go in and manipulate these values within reason. There's typically a starting point that we like to see these values within range. So we're going in and manipulating these fractions and ratios to try to get something that matches up to the overall observed hydrograph. This is a widely accepted process. It's great to help with our modeling inputs, and just about with anything, the more experience you have going through this process, the quicker it can be. So what are we trying to do with this data? Trying to quantify base flows for our dry weather periods, establish our peaking factors, how much I&I is in our system, project out theoretical rainfall events to understand capacity limitations, future planning if we want to expand to handle a larger frequency event, maybe understand some of the I&I reduction that we get from pre and post flow monitoring from rehabilitation, determine our criteria for model inputs, and evaluate limited capacity locations. Jumping into capacity evaluation, some of the basics, what are we trying to design for? Average daily flow to handle the low flow periods, daily flow plus infiltration. So kind of a normal spring month, maybe the groundwater is elevated and we're handling that small fraction of excess clear water with our wastewater production. Then peak flows, looking at RDII plus all the above. So how does our system respond under all those scenarios? Mannings Equation. Not going to go into a whole lot of depth with this, but if we steepen up a pipe, it's going to result in more flow capacity of that piping system. And one of the things that make this difficult to employ on a larger scale, we're doing a system-wide capacity evaluation. The iterations that it would take to do all that by hand are just almost unimaginable from an effort standpoint.
Thank you for listening to Snyder Associates podcast series, a civil engineering, planning, and design firm focused on thinking beyond engineering to improve quality of life within the communities we serve. Find content related to this episode on Snyder-Associates.com.